Thanks a lot for the invitation. I will give you a talk about distributed games and present you some decide positive and negative results in terms of computability of those games. And yes, there is a strong link with the work of Paul because, to my opinion, he asked the right questions, the most interesting questions, and he gave some partial answers. And that was a beginning for a road of work of myself and other co-authors. And so thank you, Paul. And I will try to share my enthusiasm about your very brilliant idea in this talk. Okay, I cannot change the slide, so okay. I can. So the talk is about distributed controller synthesis that I will give you, of course, the background and the definitions to understand exactly what is the problem. But let's say from now that there are two ways to consider a distributed controller synthesis when you are from the automata community. You can consider the control problem with local view, à la Pnioli-Rosner, and control problems with causal view, à la Paul-Gastin. And from those two perspectives, I will give you positive results, negative results, and also share some open questions for further work. So the generic question about distributed controller synthesis is that we are given a controllable distributed system. So distributed in the sense where this is not a centralized system. There are several components which interact together. And we want to control this distributed system. I mean, we want to compute a controller that will control the system and guarantee some property. The most basic one being that there is no deadlock. Okay. You can think of examples like servers on a network, a plant with several machines that interact together, and so on. I will not give a lot of practical examples because I don't have any, but maybe some days there will be some. And you want to control your plant, and to add a bit more of fun, there is some adversarial non-determinism. So you cannot control exactly what will happen. You can control partly what will happen, but there may be also some events that are uncontrollable, that are, like, for example, a failure of a machine or a disconnection of the network, maybe temporary, and so on. And of course, if there exists a controller, so you are happy to know it, but you want also to compute the controller, to being able to compute your plant, your system, your computer, your network of computers, and so on. Okay. So that generic presentation of the question opens two sub-questions. What is a controllable distributed system? And what is a controller? So I will show you the notions one by one because this is an interesting topic, but it's a bit technical. So it's hard to share all the notions like in 1 hour, but I will try my best to. So we will start with something very simple, just one process with two controllable actions, okay? So is there any pointer or something? No. Or maybe with the, can you see my mouse? Yes. So there is this initial state here. Wow, so many. Thank you. No, Patricia. So there is this initial state here. Okay, there is a single process alone. And it starts in this initial state. It can play 0 and stay there, or it can play 1. And this is not a very good idea to play 1 because if it does so, it reaches a deadlock state. There is nothing more to do. Okay, so what is a good controller in this case? The controller will say, never play 1. Okay, stick to 0. This is safe. There will be no deadlock. Okay. Now let's add some uncontrollable actions. So here you have still the controllable actions in white and the uncontrollable actions in red. And you start in this initial state. And here you will not be able to choose between left and right. And you see that, again, you want to avoid these deadlock states. And your strategy will not be to always play 0, but to play 0 if you are moved to the left by the environment, and play 1 if you are moved to the right. Okay. Again, the winning strategy is easy, but you have to adapt to the environment. And now, if I make this action uncontrollable, there is no winning strategy anymore, because simply I cannot avoid that the environment does a right and a 0 immediately afterwards. There is no... the environment can always preempt. Like, if it decides to play an uncontrollable action, you cannot do anything. So here, you will say, I would like to play 1. No. You go to 0 and you lose. Okay. So 3 examples already. So as long as you stick to one process, this is not very distributed for the moment, with controllable and uncontrollable actions, you're actually, there is an analogy, it's almost the same as 2-player zero-sum games on graphs, finite graphs, with safety winning conditions. Okay, so this is from the games the game on graphs community. This is a trivial class. From a computational point of view, in polynomial time, you can compute the winner, compute a winning strategy. This is well known. This is harder if you replace safety by parity, but it is still decidable. The exact complexity not being really known for the moment, but this is another topic. Okay, now let's connect processes together. So to connect processes, we will introduce shared actions. An example here, there are still local actions, LA, RA, LB, RB, here, and there. Those are local. But now the 0 and the 1 actions, they are shared. Why are they shared? Just because they appear in 2 processes. As soon as they appear to 2 processes, they are shared. And when an action is shared, it has to be played at the same time by the 2 processes. Okay, they are synchronized with those actions. Okay, okay, that's it. Do I have anything interesting to say about this example? Maybe let's see on the next slide. Yes, okay. So how would the processes play? For the moment, there is nothing uncontrollable. So they can agree, for example, on the first action to play. Of course, none of them want to deadlock, okay? The controller wants no deadlock in either process. Okay, so they have to agree on the first action. Both of them should play LA and LB, or RA and RB, so that in the sequel, they can play both 0 forever, like here, or 1 forever, okay? So this is a representation of the winning strategy, part of it. You see, this is a usual representation of traces and stuff like that. You have one horizontal line with one process, PA, one horizontal line with the other process, PB. And then you have those actions which are not connected because they are local. And when 2 actions are connected, it means it's a shared action. When 2 dots are connected, it represents a shared action, okay? And that way, controller wins. And of course, it's not represented here, but in the back, there are states here. So initially, states IA, then playing this local action, we go to state LA, and then we stay there forever. Okay. Most of the time, I will not represent the states, but somehow they are there, right? Now, if I make those 2 actions, LA and RB, uncontrollable, of course, again, there is no more winning strategy because the environment can fire them, LA and RB, like here, tac, tac. Now the 2 processes are in state left for PA and right for PB. And maybe they will be able to play 1-0 together, for example, but then they will one of them will deadlock. Okay, in this case, this one goes to say DB and is deadlocked. Okay. So just a word about the setting. The setting is deterministic in the sense that transitions are deterministic. Formally, an action A is synchronizing a set of processes DOM like domain, DOM of A. It's represented as usual as the tuple of states of the different process, the action, and the tuple of new states of the processes. So it's a really what is called also asynchronous automata, automaton, Jilanka automaton. It has several names. Why do we choose them deterministic? It's just by convenience, because the sequence of actions determines the execution. So to describe the execution of the system, we just have to tell which actions were played, and we don't need to bother with states. Okay. Yes.
The previous slide.
Yeah.
Even the previous one. If exactly LA and LB are red.
Yeah.
Does the controller lose? It's just a question.
No, they win. They win because their strategy will be to allow only LA and LB. Okay. I have not formally defined. That was actually my next slide.
Okay.
What is a controller? It's a bit fuzzy for the moment. I have defined what is a controllable distributed system. So it's a deterministic asynchronous automaton with uncontrollable actions. I have not defined what is a controller, what is a strategy. So let me answer by it. So let's look first at the control with a local view, which is not the invention of Paul, and I keep the best for later. So in the local control question, there is one controller per process. And this is also the case for causal control, but with a local view. It means that the controller of a process, it can only observe what happens locally in the process. He has no clue about what happens in the rest of the system. Okay. So in my example, the controller of PA on the left has no clue of what is happening on the right with PB. Okay, and conversely. Formally, a controller can block controllable actions, can prevent them to happen. It cannot block uncontrollable actions. Okay, that's the way how is defined a controller. And if you want to be even more formal, this is a local strategy is a map, sigma, like sigma is often used for strategies, from sequences of actions of the process. You remember that sequences of actions that determine actually the whole run of the system because we are deterministic, to set of actions. And in this set of actions, this is what the controller the only actions that the controller will allow to occur. And he has to include all uncontrollable actions. This is the constraint. Okay. So if I can go back to your question and to this example. So you were asking if LA and LB are red and the other are right. Yes, there is a winning controller. It will allow only LA and LB. So it will be for sure go to state there LA and LB and play 0 forever. Okay. Okay. So yes. Yeah. No. No. Not at all for the moment. Okay. I did not invent that. This is Tunele-Rosner. I think that distributed synthesis started like that. Yes. Okay. So sometime in the past, they were very happy with that notion. Yes, there is no flow of information. Albeit there is no flow of information, this setting is actually very expressive and powerful. I will show you why. So now for a few slides, we will stick with this example where I have a left process, a right process, and a controller in the middle. And we will progressively create the controller together. So those actions OL, 1L, OR, 1R are controllable. Okay. You see that those processes are very simple. They're just one state. Okay. And so the strategy of a local controller is just a word, actually, because every controller here of L, I'm not speaking about controllers of C, but controllers of L and R, they just see what happens locally. So they actually they just observe their own actions, and that's it. And their strategy is basically a word. There is no outside events to react to. So In general, the strategy is a tree because you react to what the environment will do, but here the environment does nothing. So it's just a word, okay? So the strategy for controller L is a word UL as a sequence of letters 0L and 1L, infinite, and the same for R, okay? So now I would like to design a controller which enforces both words to be equal. This word here and this word. Of course, up to renaming, okay, so I drop the indices L and R, and I want the sequences of 0 and 1 to coincide. Well, this may require maybe a bit of thinking, but it's an easy exercise. Whose solution I hope is there, because I just drew it in the train before coming, but I think it's this one. The controller will start in this initial state. It will first it will first synchronize always with L, either on 0L or on 1L, okay? And it will just record the action chosen by L. And then it will synchronize with R on the same action, meaning the same with the same 1 or the same 0, okay? Just like this. For example, 0L, 0R, 1L, 1R, BL in general, BR, okay? And that's it. And this enforces both words to be equal. Yes? Okay, good. So this one was easy. So you can test equality of two words. Now you will see where I want to take you to. I start with the PCP instance, post-correspondence problem, with, let's say here, two pairs of words, U0, V0, and U1, V1. And I want to design a controller which guesses sequences of indices of the PCP problem. And which want to match the output of L. Okay, so he wants UL to be equal to UI0, UI1, and so on. Again, this is an easy exercise. Basically, what the controller can do, it will never synchronize with R because the specification is not about R. It will always synchronize with L. And it will guess the indices one by one, first I0, I1, I2, and so on. And in between, it will synchronize with L on the right word. So if it's a 0, the first instance is 001 here, 001. If it's a 1, the first instance here is 1, and so on. Okay. And now, if you combine those two ingredients, actually there are three because you have to do the same for the other process. Okay. You can reformulate the post-correspondence problem as the existence of a controller, which checks that the left words and the right words are equal, and that they correspond to a PCP solution. Okay. And simply the trick is that initially the controller will non-deterministically check either the first condition or the second bis. Okay, the second for L, the second for R. Okay, and since there is no communication, there is no information flow. Both processes L and R, they don't know in which checking mode they are, and they still have to output the same word. And this enforces all what is required to encode the PCP problem. Okay, so you see, that's bad news somehow for distributed synthesis, because now the most basic problem is undecidable with three processes. Both of them, two of them, they have one state, and the other does not have many states on top of that. So it's a catastrophe. And this is a catastrophe, but it's also a theorem. So stated by Pinelli-Rosner, but somehow you can find it in the work of Reif also. Distributed synthesis is undecidable. So I will stop my talk because it's undecidable. Bye. When controllers have local view, that's where Paul enters the game and introduces with co-authors controllers with causal view. So again, local controllers, they are stick in their box, they don't see anything, but it's not very fun, okay? Because you want to work as a team, and as a team, you want to communicate. That's why, I don't know if that's why, but that's a possible motivation for Paul, Benjamin, and Mark, which is here also today, to have introduced controllers with causal view. Controllers with causal view, they can communicate. They don't have all information about the distributed system, Otherwise, somehow it will not be a distributed system anymore. But they can communicate when they synchronize on an action, which makes sense. Okay. So they synchronize on the action, and they can have a chat, exchange as many information as they want, including strategic information for further decision making in the future. They will be able to use it based on the information they did exchange upon synchronizations. And what is cool with this notion, it breaks down the undecidability proof. At least you cannot keep it that simple. Why? Because if I want to do the same undecidability argument with causal view, no, I cannot anymore. Imagine that the controller C, he wants to check whether the left and right words are equal. So, okay, he will say, okay, I will check that. He synchronizes with L on a letter, okay? But now he can tell L that he's doing that. Okay, so here it's red because actually the environment choose in which checking mode we are, okay? So the environment will put C in checking mode UL equal to UR, but C now will reveal it to L. And the same when it will synchronize with R, it will reveal it to R, okay? And now the two processes, they can output any word, any pair of words, as long as they match. They don't care anymore about the PCP instance. Okay, they are, for example, they can output 0, 0, 0 forever. It's okay. Okay, and the same for the three modes. So you see that with causal view, with communication, you cannot encode PCP that simply. Okay, alors, control with causal view. Let's talk a bit more precisely about what is control with causal view. So first, there is no global clock. Okay, you are only interested in causality in your system. It means that when two actions happen in two processes without causality relation in parallel, there is no date. We don't know exactly. There is no notion of when was before the other or not. This is how can you formalize that? First, with commutation. So you represent runs of your system as Mazurkiewicz traces, for example. So here you see that A and D, they are disconnected and they can commute. So actually AD-AC and DA-AC is the same. And AADC is the same. All those guys are in the same equivalence class. Okay. But letters C and D, they do not commute because they share a common process. So AACD is not the same behavior. We would have to put the D here and it cannot commute. So it's not the same execution. Sorry, I'm a bit quick on that because yeah. Probably many of you in the room knows that already. So I have to find the right balance. And I have to introduce also, to be precise, the notion of causal past, the view of a process. So here, for example, you have a run of L, C, and R. And here is the causal view of L. What does he know about that? For sure, he knows his own action. Yes, those three, because they are already in its local view. Of course, causal view is larger than local view. He also knows that because C and R, they did communicate together, they did synchronize, and afterwards, C, he did synchronize with L. So L, here they could have a chat, and L could learn about this action. Okay, so all this is in the causal view of L. And this is not because there is no information flow from those events to the actions of L. Okay, let's keep it intuitive like that. Otherwise, you can say that it's the shortest, no, it's the longest. You take the trace, you decompose it in a product of trace. The first should be prime, and the second should be only made of actions parallel to the process. Well, there is a formal definition, but you have the idea, I hope. And if you don't have it, please interrupt me. Just another example. Again, we will compute the view of L, the first one. So here we will take the last action, which was synchronizes L and R, but not this one. So you see, sometimes causal view is not convex. It's a joke, but You could move this here. It would be the same trace. Somehow it will become convex again. So now how can we formalize the strategy of a process with causal view? Strategy of a process. So with local view, it was a mapping from sequence of actions to set of actions. With causal view, it's a mapping from traces, prime traces actually, whose maximal action is contains P in the domain, to set of actions. And the rest is the same definition. Okay? It's just the input of the strategy which changes. But again, we have uncontrollable actions. You cannot restrict them. They can happen whenever, blah, blah. Okay. Okay, and we want, of course, winning controllers, which are controllers such that there will never be any deadlock. Whatever the environment does, whatever the uncontrollable actions are chosen, there will never be a deadlock. Okay, so now, yes. A prime trace is a trace with a single maximal action. But first, I'm a noob in Mazurkiewicz trace theory. Second, you really need a half an hour on the board to understand the notions and stuff. Third, you can ask to Paul. I'm sorry, I will just keep on the intuitive level, but okay. Many people are specialists in the room of Mazurkiewicz traces, so don't ask me. So we started with this negative result about local control. And then it was very depressing. So it was for 14 years. And then come Paul and Benjamin and Mark, and they invent this notion of distributed synthesis with causal view, which is really cool because you are in a distributed system. You want to work as a team. You communicate. They asked this very interesting question: is controller synthesis with causal view decidable? And they said yes, in a particular case for series parallel game, but which was already a very large class. It's a very nice class in which you can already design many interesting distributed systems. So this was really, I think, a major result. So thank you, Paul. And very inspiring. And then there was a series. So I think people were interested in this question, decidability of synthesis with causal view, because there was a result of Madhusudan, Tyagarajan, and Yang. It was actually about logic. I will not speak a lot about logic in this talk, but their result about logic implied that distributed synthesis was decidable for another class, connectedly communicating games. Okay? And then we worked with Blaise, Anka, and Igor, and we proved that the answer was yes also for another subclass, acyclic games. Then I was trying to prove that it was yes for all games, all distributed games. But I could not do it, so I was only able to show it for decomposable games, which was a superset of these three classes. Okay, and finally, no, it's not decidable. Sorry, it's a bit disappointing, but yeah, that was yeah, that's a series of results. A lot of time spent on those problems, thanks or because of Paul. I don't know how to, but yeah. Yes, question. Is decidable with 4 already in this paper for 4, and for 5 I don't know. There was an intern coming from Chennai. He suffered on the 5 case, and we didn't have a definitive answer after that. So it's still open for 5 processes. Okay, let's. How much time do I have? Okay, good. I have to speak. Combien? Un peu plus de 15 minutes. Okay, perfect. Let's just have a look at the positive result, the decidability result. So there were four of those for series parallel game, connectedly communicating games, acyclic process graphs, decomposable action graphs. So in all those papers, in the end, it ends up by constructing an upper bound on the memory needed by controllers to win the game, if they can. Okay. So you put an upper bound on the complexity in the class of controllers that you look for, of winning controllers you look for. So it puts a bound on the size. You can enumerate it, and if it's empty, okay, it's you can decide it's empty just by checking at the small elements. If they are small. Small is not the right word because in this paper it was shown that the complexity of the problem is non-elementary, so it's not a small set. And all those guys, all those results are not practical. All the complexities are awful, I think, even if you work, I guess, yes. But it's more like decidability results. Okay, so A and C, the first and the third, they put a structural restriction on the information flow in the system. And based on that, you can perform an induction because the restriction is inductive. So you do the same induction on strategies and you extract upper bounds. It's technical. B put an upper bound on the length of information forks, not on their structure, but on their length. D tries to generalize it, but it's very in an unpleasant way. So don't read this paper. But it uses strategic shortcuts. Whose philosophy, if you can do it now, why doing it later? Okay, so this philosophy is easy to apply if you are on your own. Okay, if I can do something now, why would I do it tomorrow? Okay, let's do it. Okay, but if you are a team and you want to do it now instead of later, you have to tell the other guys. But in the team, you cannot synchronize everybody at the same time. So it's harder to implement this paradigm in distributed synthesis and in single process synthesis, but you can do it. Okay, so now I will just end the talk by trying to show you why control with causal view is undecidable using 6 processes. So one of the basic ingredients, is those 3 processes here. T0, T1, T2, that always interact in the same way. First, T0 and T1, they connect. Then T1 and T2 connect. Then T0 and T2 connect. And again, we start again. T0 and T1 connect. T1, T2 connect. T0 and T2 connect, and so on. There may be, it's not always the same action, but it's always the same communication pattern, okay? And we take, and there is no concurrency here, no 2 letters commute. So basically, it's almost a word and a simple automaton. Now we take 2 teams of those guys. So we take team top, T0, T1, T2, and team bottom, B0, B1, B2. Okay, and they do the same in parallel. Always the same pattern. Okay. And the environment, for the moment, it did nothing, but it can challenge. It can challenge the processes. So I will show you what we can implement with challenges. Here, it will interrupt T2 and B2. So you see they are in 2 different teams, but they have the same index here. He's interrupting them, and he's asking a question. Do your histories have the same length or not? Okay. So here the answer would be yes, because the history here is 1, 2, 3, 6. Your history in let's say your local history, so it will be 4 here and 4 here. So the answer would be yes. Yes, they do. They gave the correct answer. In this case, the answer would be no, because here it's 4 and here only 2. Okay. So for the moment, I have no way to enforce processes to give the right answer. Okay, but actually we can do it. Thanks to the causal view. First, thanks to the causal view, the processes are able to give the right answer. They know the right answer. Why? Because when they are synchronized by the environment here, they can share information about their past here and here. They can exchange that, know its common knowledge, and they can compute the answer yes or no. They can do it, but for the moment, there is nothing to enforce them to do it, okay? But they can do it. So now let's try to enforce them to be truthful, okay, to give the right answer.
How do they count the length?
No, not the, here. Yeah. You see, a strategy is a very powerful object. it can take as input. So in the local case, it's words of arbitrary length, and here it's traces. So in general, a strategy is not something computable. It's just a mapping, a general mapping from traces. So here it's a whole trace, right, to a set of letters. Okay. Of course, when we want computability results, what we like is to have finite set of strategies with finite memory. But in the general definition, here, if they are very smart, if they are Turing smart, I had a debate with Igor because for him, controller synthesis is asking about a finite strategy. But in general, when you are able to answer the question about the existence of a winning strategy, it's more or less the same than the finite one. But let's be careful. Okay, but for me, I don't want any restriction like that. Okay, I just want existence of a strategy, whatever it is, even if it's not finite memory. Okay, so yeah, so again, when they are here, their causal view is everything before, so they can compute the answer, the correct answer. So let's try to enforce, force them to give the right answer by just adding, not adding too many power, just a few actions and a few transitions. So here is a trick. And if you understand that, you understand the whole proof. It's very simple. You do parallel challenges here. So at the same time, the environment, it will stop T2 and B2 here and ask them the length question, is it the same length? And it will do the same with T1 and B1 at the same time. And here, those two groups of processes, T1, B1 and T2, B2, they don't know that they are checked, whether or not they are checked in parallel. They don't know that, okay? Because this red and green guy is actually totally parallel to this red and green guy. You see, we could commute them, okay? And then the environment can check the consistency of the two answers. Because they should give the two pairs of processes, they should give the same answer because he interrupted them at moments which are almost the same. This can be encoded with finitely many states. So now it's checking the consistency. If the environment ever detects that there are inconsistent answers, it will deadlock them violently and they will lose. Okay. So to win, they have to be consistent between two consecutive answers. But now we can propagate this constraint. And since this and this should be consistent, and now this and this should be consistent, and we can actually go back to the moment where at the beginning, the right answer is none, because we can hardcode that the answer is 0 here, that this guy is 0 and this guy is not 0. Okay, so we can hardcode the right answer whenever one of the processes has never played. Okay, and so we can hardcode it at the beginning, propagate it in the future, and now we can enforce truthfulness like that. Just because you never know whether somebody will be checked in parallel or not. So in the doubt, you have to say the right answer, always. You have to be truthful. Okay, so now, you see now we can compare numbers. So we can always encode PCP. I mean, it's you can see that it's powerful. So you can encode PCP directly, or you can encode another problem, which I try to invent to make the proof easier to read. It's the bipartite coloring problem. You have to color this ladder of points with colored edges, and you have to be consistent with some patterns that are forbidden. It's not a big deal, but this problem is clearly undecidable. You can encode PCP in there. And now here you can see that it's almost like synchronization of processes. So instead of asking them whether the two lengths are the same, we will ask them for the color of the edge. Okay. And this is then the same. So what is the color here of edge 7, 5? Okay, because this guy has done 7, this guy has done 5. They have to answer the right color. They are checking consistency, blah, blah, blah. In the end, you encode PCP. Okay? So this is why it's undecidable. So distributed synthesis is really undecidable with local view, with causal view. There are still open problems. Decidability with 5 processes. Decidability for weakly connectedly communicating systems. It's It looks like the Madhusudan-Tyagarajan class of systems, but a bit more general. Still, we need decidable models for distributed concurrent synthesis. For example, there are real-world problems like bugs in the glibc. We need probably to develop models that are closer to what people do when they program, when they do programming with concurrency. It's not easy to do. There are many works that did not cite about that. But, okay. And there is another interesting open, or at least research direction, is to study the problem with mixed strategies that can use probabilities. And probably the decidable results can be extended to a quantitative setting where you don't look for exact controllers that win for sure, but controllers that can maximize the probability to win or win almost surely. So thanks for listening, and voilà, that's it.
Do you know of any relevant variants of distributed synthesis? I mean, models for that. Not causal view, not local view, but something different. You know?
Not really. There are other models that I did not speak about, like Petri games. Sorry, but they are more or less equivalent. Well, but classes of controllers, I don't know. Interesting ones, I don't know. But you can invent a new one like Paul did, maybe, and it will be my guest.
Yes, question. So you said that controllability is decidable, so series parallel.
Yeah.
But undecidable in your case. I did not see how your example is not series parallel.
Ah, good. Excellent question. So it's not, I can tell you first why it's not weakly connectedly communicating, because the two teams of processes, they can play for arbitrarily long time without communicating and then communicate, which is forbidden, okay, with this class. And now why it's not series parallel? I never asked myself this question. Paul, you know?
Where is the
I hope it's not. Otherwise, we have a problem. So you would like to build this alphabet. Do I have a better? Yeah, like this one. Using only series parallel operation. It means that you can either take two alphabets and take their union, and the letters can fully commute, or you can take two alphabets and the letters cannot commute at all, right? Okay. Yes. We want, yeah, I think it would be hard to do because we want those meta checks, those parallel checks, we want them parallel. And when you are about to add them, I think you would be in trouble. At least if you build your alphabet in the, I think in the natural way, like first this one, then this one that takes the union, or add the parallel check, I think you are in trouble. Yeah. What is a P4? Ah. I think that's a much better answer. Yeah, thank you. Totally precise reason that it's not series parallel. Yes, you're right.
I think one question was if you have a winning strategy. I mean, do you know a system where you have a winning strategy, but no finite memory winning strategy?
Not for reachability problems, because by design it's finite. No, no.
So the problems are the same in that case.
Yeah. Probably we should ask that to Jérémy Chalopin. No, he's the top guy to find complicated instances. Okay, thanks for the question.
So at some point you suggested that when processes communicate, they can talk about what they're going to do, what strategy they will use. And so have you ever seen this happening? Because, I mean, in what you were telling, it was always about what happened so far, about,
yeah.
You know, and even the strategy is just a function of what happened so far. So I wonder how they can generate information.
The decidability problems, the proofs of decidability are more fun in terms of strategies, because here the strategies are really restricted. It's just like comparing numbers. From here, at least here and there, and also I think in Paul work, you can reread the proofs or rewrite them in a way that actually you have teams of processes which agree on a strategy to use together. Okay. And for example, in this case here, you have a leader in the team, and when he meets another leader, they will agree to a new strategy to propagate in their community. So they are really settling and negotiating about what strategy will play in their community. So maybe it's closer to what you were thinking about. Yes.
Long live India and France friendship.